Welcome to lesson 1.8 on solving exponential equations by graphing, and we're going to be using technology for this. So make sure that you have Desmos available to you. Sit back, enjoy the ride, and we will begin. So just to recall, our exponential equations had this format of y equals ab to the exponent of x. And remember the a, that is your initial value, your beginning value. You're starting your value or your y-intercept, initial value. And the b, of course, is your base. It is the amount of 1 plus or minus the percent growth or percent decay, depending on whether it is growing, of course, or decaying. So this is always your base. It's going to be 1 plus the percent growth, or it would be 1 minus the percent decay. So that you should already know from previous lessons. If not, you should get working on putting that into your brain. All right, just before we begin some of these applications, some of the applications do involve the compound interest formula, which was new to you in grade 11, but it is no longer new. So it does follow that overall format in terms of P. P is like the A, it is your initial value. And when we're talking about compound interest and money, that P stands for the word principal. And the principal is your initial amount of your investment, or the initial amount that you are borrowing. Okay, the amount initially invested or borrowed. Now, when we're talking about this I value, it is the percent, it's your interest rate per compounding period. It's your percent per compounding period. So you already have the one that's here that we've talked about earlier on, plus the percent, the interest rate, or your percent, interest rate per compounding period. So, for example, if you have an annual rate, your I value is just going to be that annual rate. But if you had your interest being compounded semi-annually, it means it's compounding twice per year. You would take your annual rate and divide it by 2, because there's two. It needs to be broken up into 2 pieces over the course of the year. If it's compounding quarterly, you would take your annual rate and divide it by 4, and that would be the value you would use for I. If you're compounding monthly, take your annual rate, divide by 12, and that would give you the value of I. So it's always your annual rate divided by the number of times it's compounding in 1 year. Okay, so that says I is equal to your annual rate divided by number of times compounded per year. All right, the last thing we need to identify here is this value, or this exponent of n. Now, n is the total of number of times it's going to compound. Now, sometimes people like to keep n as representing the number of years. So if it's compounding yearly, n would just be n. But if n is their number of years and it's compounding semi-annually, you would take the number of years and times it by 2. So you could put a 2n as your exponent, where n would be the number of years. But in the end, the overall exponent has to represent the total number of times it's going to compound. Okay, so hopefully this will make sense as we go through an example here. Audrey invested $1,000, so that's her starting amount, at 9% per annum per year. Annum just means per year, compounded annually. So it's just once per year. Her daughter invested $2,000, so this is a different investment, $2,000 at 2.5% per annum, but this time it's compounded semi-annually. How long did it take for the investments to be of equal value? All right, so I've broken this down into steps here. Write the equation for the amount of Audrey's investment. So Audrey's investment amounts to, starting with $1,000, it's increasing at 9% per year compounded annually. So we're just going to add 0.09. We don't need to do anything specific with that. And I'm just going to leave that to an exponent of n because it's just compounding once for every year. So n represents my number of years. Now, Audrey's investment, we are going to look at these together. So our A is our amount over time. That's what A is. Our N is representing our number of years here. So if I work this in, Audrey, her amount starts at $2,000. So her graph is starting on the y-axis at 2,000. But her interest rate is 0.25% per annum compounded semi-annually. So I'm going to take that 0.025, that 2.5% per annum, but I'm going to divide it by 2 because it's compounding twice every year. Now, as far as the exponent goes, if n is representing my number of years and I want to be able to compare these, I am going to have n, but I'm going to multiply that by 2 because for every year it's compounding 2 times each year. So 2n would give me my total number of times compounded overall. Now, what we're going to do is use our Desmos here. We're going to put these into Desmos. The A is like the Y, and your N is like the X. So think of the A as the Y, and your N is really like the X. Put those into Desmos. So Y1 would equal 1,000, bracket 1 plus 0.09 to the exponent of X, and then do a second equation of Y equals 2,000, 1 plus 0.025 divided by 2 to the exponent 2n, and find where the intersection point is. Okay, so put this on pause, put that into Desmos, see what happens. You might need to put brackets around that 2n to make it work. I'm not exactly sure, I can't remember. And then find your point of intersection. Okay, if you found your point of intersection here, you should have gotten an ordered pair of 11.301, provided I put it in correctly, and comma 2648.34, roughly. Okay, now the question in part E is, explain the significance of the point of intersection in relation to the question. So this represents my X or my N. N is the number of years. So after 11.301 years, their investments are equivalent to each other and they're both worth $2,648.35. Okay, after 11.301 years, or 11 years and 3.6 months, the investments will be equal in value. And if you're wondering how I got the 3.6 months, what I did is I took the decimal part, 0.301, and I times that, or multiplied that by 12, since there's 12 months in one full year. So I want this decimal amount of the 12 months, and that gave me my 3.6 months. So just a little over 3.5 months. A little less than 4 months. All right, moving into the second page here, or example number 2. Bailey has saved $5,000. He checked the website of a bank, blah, blah, blah. You can read this question, get an equation for Bailey's investment, get an equation for Candace's investment, find the intersection point, do the interpretation. See if you can do that for number 3 as well, and then I will take this up with you. Okay, so I have my equations for both Bailey's investment and Candace's investment. Remember, because Candace's is being compounded quarterly, we take the annual rate and divide by 4. We also take the n number of years and times it by 4 because for every year it's going to compound 4 times. I found my intersection point, and that means that both investments will be equal after about 30 years, just a little more than 30 years, at a value of $15,545.76. And again, I hope I entered all my information into Desmos correctly. All right, put it on pause again. Try the third example if you haven't done so already. All right, this question's slightly different in that we want to know for how long it will take for his investment to double. Well, in terms of this, our equation for David's investment is compounding monthly, so that's why I'm dividing my annual rate by 12, and I also have my n being multiplied by 12, so n represents my number of years. And my equation 2 this time is not another investment, it's just y equals 2,000. I want to know when that investment doubles. So my investment amount, my A value, is going to equal 2,000. When we look at these in our future unit, not this unit, but really what we're looking at, whoops, let me try that again. What we're really looking at is solving the equation of 2,000 equals, let's try that again, equals 1,000, and then we have our 1 plus 0.072 divided by 12, all to the exponent of 12n. And we're solving that for n. We're going to look at how to solve this algebraically, but our only options right now are either through guess and check, like trial and error, or using Desmos to solve these. Next unit, we get to learn how we can work this backwards algebraically. All right, continue on with the next examples, and then you can check with the next video.